Usually, when we talk about the human body, we tend to think of it in purely biological terms,
Right,
right?
sure. Yeah, blood pumping, lungs expanding, muscles contracting, just biology.
Exactly. We view ourselves as these like organic wetware machines.
Hmm.
But taking a really close look at the physics of electromagnetism completely reframes that image.
It really does. It changes the whole paradigm.
Because right now, as you sit there listening to this, the incredibly faint electrical impulses traveling along your own nerve cells are generating an actual physical magnetic field inside your body,
Yeah, it's wild to think about. You are quite literally a walking, breathing electromagnet.
which is just mind-blowing.
Right. I mean, every thought you have, every little movement, it sends an ion current down a nerve. And every single one of those microscopic electrical currents is surrounded by its own invisible magnetic halo.
It fundamentally changes how you look at yourself.
Mm-hmm.
And honestly, it changes how you look at the room around you. So welcome to this deep dive into the hidden forces that are powering our modern world.
Glad to be here.
Our mission for this deep dive is to really demystify electromagnetism. We want to take these dry textbook concepts and ground them in reality, focus on the mechanisms that run the technology you interact with every single day.
Exactly. Everything from the toaster sitting in your kitchen to the life-saving MRI machine at your local hospital.
Because the exact same physical laws governing those tiny magnetic fields in your nerve cells are what allow us to generate the massive amounts of electricity needed to run an entire city.
Yeah, it's all connected by just a few fundamental rules of physics.
So whether you're reviewing this material for a big physics presentation or you're just insanely curious about the invisible architecture of the universe, we're going to look right past the plastic casing on your appliances and see what's actually happening.
Sounds like a plan.
But to really grasp how our own bodies generate magnetic fields, I think we have to rewind, right? We need to go back to the moment humanity first realized that electricity and magnetism were even related.
Oh, absolutely. We have to go back to the year 1820.
Okay, set the scene for us.
So there's this 19th century Danish scientist named Hans Christian Ørsted, and he was conducting what he thought was a completely unrelated experiment.
Just a normal day in the lab.
Right. He had this simple metallic wire running across his lab table, and he passed an electric current through it. But sitting nearby, just by chance, was a standard navigational compass.
Oh, wow. And what happened?
Well, when the current flowed through the wire, the compass needle suddenly deflected. It physically moved, pointing completely away from true north.
Okay, let's unpack this for a second, because historically, electricity and magnetism were thought of as two entirely separate forces.
Oh, yeah, like totally unrelated. Lightning in the sky was one thing, and the magnetic lodestones that helped ships navigate were another.
So finding out they're intertwined like that.
It's a massive shock.
It's basically like finding out two of your friends who you thought were total strangers have actually been secretly married this whole time.
That is a great way to put it. And that hidden relationship, that little deflection of a compass, built the foundation for the entire modern world.
Wait, really? Just from that one observation?
Basically, yeah. I mean, radio, television, fiber optics, global power grids, literally none of that exists without the realization that electricity and magnetism are two sides of the same coin.
That is incredible.
His contribution was so monumental, actually, that physicists named the unit of magnetic field strength the Ørsted in his honor.
That's quite the legacy. But let's think about the mechanism of that compass for a second to really understand what happened.
Sure.
A simple compass is essentially just a tiny bar magnet suspended in liquid
Right.
or balanced on a pin, right?
What's fascinating here is that, yes, it's just a tiny magnet. It has a north-seeking pole and a south-seeking pole.
And the fundamental unbreakable rule of permanent magnets is that, like, poles repel and opposite poles attract,
Exactly. A north pole pushes away another north pole, but pulls a south pole toward it.
which means for the compass needle to violently deflect when Ørsted turned on the battery, the wire itself had to be acting like a magnet.
You nailed it. The flowing electric current generated its own temporary magnetic field in the air right around the wire. And that invisible field pushed against the tiny permanent magnet inside the compass.
It's one thing to know there is a field there, but it's another to, like, visualize it. Because a
Wow.
magnetic field isn't just an amorphous cloud of energy, is it?
No, not at all. It has a very specific architecture. It has magnitude, meaning strength, and a clear direction.
So how do we actually see that architecture?
Well, you can see it with a really classic experiment. If you place a standard bar magnet under a sheet of paper, right, and then you sprinkle iron filings uniformly across the top.
Oh, I think I did this in middle school. The filings don't just sit there.
Nope. When you tap the paper gently, the tiny pieces of iron experience the magnetic force, and they automatically arrange themselves into this sweeping geometric pattern.
They align themselves along the magnetic field lines.
Exactly. And these invisible lines follow strict traffic rules.
Like an invisible, perfectly organized highway system.
Yeah, a highway system where they always emerge from the north pole of the magnet, loop around through the air, and then merge back in at the south pole.
And what happens inside the magnet itself?
Inside, they actually travel from the south pole back to the north, which creates continuous closed curves.
Okay, that makes sense. But the pattern formed by those filings also reveals the strength of the force, right?
Yes, the relative strength of a magnetic field is dictated by the degree of closeness of the field lines.
So crowded lines equal a stronger force.
Exactly. Where the lines are highly crowded together, like right near the physical poles of the magnet, the field is at its absolute strongest.
And if you placed another magnet in that dense area, the pushing or pulling force would be extreme.
Right, and as the lines spread out further away from the magnet, the force weakens.
Now wait. The source material specifically notes that field lines are never, ever found across each other. Why is that absolute? I understand they flow from north to south, but why couldn't two lines just intersect in space?
It comes down to what a field line actually represents in physics. A field line is basically the visual representation of the path that the north pole of a compass would point if you placed it in that exact spot.
All right.
So the net magnetic force at any single point in space can only have one true direction.
Oh, I see. Because if two field lines crossed and you placed a compass exactly at that intersection, the compass needle would have to point in two different directions at the exact same time.
Which defies reality. It's a physical impossibility.
Right, the compass needle can't point left and right simultaneously.
Exactly. It resolves all the forces pulling on it into a single direction, a single vector. Therefore, the field lines can run parallel, they can curve sharply, they can bunch up, but they can never cross.
That is so elegant. Okay, so we know the shape of a permanent bar magnet's field. But going back to Ørsted's wire, when we engineer a field using a live electric wire, does the physical shape of the conductor change the geometry of the force?
Oh, completely. The shape of the wire directly determines the shape of the magnetic field.
So let's start simple. What about a perfectly straight, current-carrying wire?
With a straight wire, the magnetic field doesn't form sweeping curves from one end to the other. Instead, it forms perfect concentric circles radiating outward from the wire.
Like ripples in a pond when you drop a stone. But, the wire is the stone, standing straight up through the water.
That's a perfect analogy. And just like ripples, the force is strongest right next to the wire where the circles are the tightest.
And if you increase the electric current,
The circles pack closer together, and the overall field strengthens. But as you move further away, the field dissipates.
okay, but how do we know which way those invisible circles are actually spinning?
Physicists use something called the right-hand thumb rule. It's also known as Maxwell's corkscrew rule.
Oh, yeah, this is a great physical shorthand.
Huh.
So if you imagine grabbing that straight wire with your right hand.
Right hand, very important. Don't use your left.
Right, of course. And you point your thumb in the direction the electric current is flowing, your fingers will naturally curl around the wire in the exact direction of the magnetic field lines.
It is such a simple way to map the unseen. But, humans rarely just use straight wires in technology.
True.
If you take that straight wire and bend it into a circular loop, those concentric circles of magnetic force overlap.
And as they move toward the center of the loop, what happens?
The circles get larger and larger until they appear as straight parallel lines right in the dead center of the loop.
And if you keep looping the wire, making a tightly wound coil with, let's say, 20 turns.
Well, the magnetic field isn't just 20 separate weak fields. Because the current in every single circular turn is flowing in the exact same direction, the magnetic field from each individual loop adds up.
Oh, they stack their power.
Exactly. A coil with 20 turns has a field essentially 20 times stronger than a single loop.
Which leads us to one of the most critical components in all of modern engineering, right? The solenoid.
Yes, the solenoid. It sounds complicated, but a solenoid is really just a coil of many circular turns of insulated copper wire wrapped tightly into the shape of a cylinder.
It looks exactly like a metallic slinky.
Yeah, a slinky is the perfect visual, and when you pass an electric current through that slinky, something really remarkable happens.
What's that?
Inside the hollow cylinder, the magnetic field lines become uniform, parallel straight lines. The magnetic force is identical at every single point inside that tube.
And on the outside.
On the outside, one end of the cylinder acts exactly like the north pole of a permanent magnet, and the other end acts exactly like the south pole.
Here's where it gets really interesting. We are literally forging a temporary magnet out of thin air just by twisting a copper wire into a spiral and hooking it to a battery.
And you can take it even a step further.
How so?
If you place a solid piece of magnetic material, like say soft iron, inside the hollow core of that solenoid, the intense uniform magnetic field physically aligns the domains within the iron.
So the iron itself becomes magnetized.
Yes, you have created an electromagnet.
Okay, but what is the practical point of making an electromagnet? I assume the massive advantage over a permanent one is the off switch.
That's the main draw, yeah. You can't exactly turn off a rock you dug out of the ground,
Right.
but with an electromagnet, you can instantly kill the magnetic field just by flipping the switch on the current. And you can even reverse the north and south poles just by reversing the direction of the electricity.
You gain total control over the force.
Exactly. Which brings us to the next massive leap in physics.
Well, let's hear it.
We've established that a live wire generates a field that can push a physical magnet, right? Like Oersted's compass.
The wire pushed the compass.
But physics is built on symmetry. So this French scientist, André-Marie Ampère, hypothesized that if an electric current exerts a physical force on a magnet, shouldn't the magnet exert an equal and opposite physical force back on the current-carrying wire?
Oh, the physical kickback. So the two magnetic fields, the temporary one from the wire and the permanent one from the magnet, are essentially fighting for the same physical space.
Right. They clash, and that clash creates mechanical motion.
How do you prove that, though?
With a very elegant little experiment. You take a small aluminum rod and hang it horizontally from a stand using some flexible connecting wire.
Okay, picture an aluminum rod hanging there.
Then you place a strong horseshoe magnet, so the aluminum rod is sitting right in the gap between the north and south poles.
And then you turn on the current.
Yep. When you run an electric current through the rod physically jolts. It gets pushed violently to the side.
Because the rod is suddenly projecting its own magnetic field, which repels against the horseshoe magnet's field.
Exactly. And just like the electromagnet, you have control. If you reverse the direction of the electric current, the rod swings in the exact opposite direction.
That's fascinating. And the source mentions the strength of this physical push varies.
Yes, the force is at its absolute highest when the direction of the electric current is at a perfect right angle to the direction of the magnetic field.
Okay, but how do we predict which way the wire is actually going to jump?
For that, we use Fleming's left-hand rule.
Oh, man. So what does this all mean? This is the awkward 3D physics dance move, right?
It really is, but it works. If you stretch out your left hand, so your thumb, your forefinger, and your middle finger are all mutually perpendicular to each other.
Like the 3D X, Y, and Z axes of a graph.
Exactly. The forefinger represents the direction of the external magnetic field.
Okay, forefinger is field.
The middle finger represents the direction of the electric current flowing through the wire.
Middle finger is current.
Right. And a quick note on electrons. The direction of the electric current is actually considered opposite to the direction of the physical motion of electrons.
Good to know. And the thumb.
If you align those two fingers with the reality of your setup, your thumb will automatically point in the direction of the mechanical force. It tells you exactly which way the wire will jump.
Okay, so this mechanical kick. How does this actually help us in daily life?
Oh, it's everything. That specific mechanical kick is the driving force behind the electric motor.
Wait, really?
Yeah. If you look at a ceiling fan keeping you cool, or the motor inside an electric car, or the spinning blades in your kitchen blender, they all rely on Fleming's left-hand rule.
So they just continuously run an electric current through a magnetic field to create a constant physical push.
Exactly. They turn electrical energy into rotational motion. It is the foundation of mechanical movement in the modern era.
That is wild.
And generators use the exact same principle, just in reverse. They physically spin a wire inside a magnet to create electricity. Even loudspeakers and microphones use the tiny, rapid physical kicks of a wire to create and capture sound waves.
Okay, so we are using Fleming's left-hand rule to spin the motor in a blender. But that blender is pulling a massive amount of invisible power right out of the wall to make that happen.
It takes a lot of energy, yeah.
I want to trace that power backward into the wall and see how these fields interact with our everyday environment. and ultimately our own bodies.
Let's start with the human body, actually, because it is the most delicate electrical system we interact with.
Like we mentioned at the beginning, an electric current always produces a magnetic field.
No exceptions. And the weak ion currents traveling along your nerve cells are, at their core, tiny electrical currents.
So when you, touch a hot stove, your nerves carry an electrical impulse to your brain, and that impulse produces a temporary magnetic field.
Right. Those fields are incredibly faint. We're talking roughly 1/1000th the strength of the Earth's natural magnetic field.
That is tiny.
It is. But the heart and the brain, which are these dense networks of constant electrical activity, they produce fields significant enough to be measured.
Which is the underlying mechanism for magnetic resonance imaging, right? The MRI.
Exactly. In a medical setting, doctors use massive artificial superconducting magnets to interact with the natural magnetic properties inside your body.
So the extreme magnetic field of the MRI machine aligns the magnetic resonance of the protons in your body's water molecules.
Yep. And that allows doctors to obtain incredibly detailed images of internal organs without ever having to make a physical incision.
It's just a profound use of electromagnetism. But bridging the gap from those microscopic currents in our brains to the megacurrents powering our homes, that requires a totally different scale of engineering.
Oh, completely. When you plug that blender into the wall, you are tapping into a domestic circuit.
Let's break that down. Power comes into a standard home via two main wires, generally speaking.
Right. You have the live wire, which typically has red insulation and carries the incoming electrical charge. And then the neutral wire, which has black insulation and completes the circuit.
And between these two wires exists a potential difference of 220 volts.
Right. And to understand potential difference, you can think of it kind of like water pressure in a plumbing system.
Okay, so if you have a massive reservoir of water high up on a hill and a pipe leading down to a valley, there's a huge pressure difference.
Exactly. The water desperately wants to flow down to equalize that pressure. Voltage is that electrical pressure. 220 volts is a significant amount of pressure pushing the electrons through the wire.
Got it. And when that electrical pressure enters your house, it's distributed using parallel circuits, right?
Yes, parallel circuits are crucial.
If you think about an old string of holiday lights, if one bulb burned out, the entire string went dark. That is a series circuit. The electricity has to flow through every single item in a single line.
Which is highly inefficient for a home. I mean, imagine a single river flowing through 3 water wheels, one after another. By the time the water hits the third wheel, it has lost a massive amount of its energy.
So the voltage would drop with every appliance.
Right. But in a parallel circuit, it's like digging 3 separate direct canals off that massive reservoir.
Oh, so every single appliance gets its own direct line to that 220 volt potential difference.
Exactly. The voltage doesn't drop, and every appliance can operate on its own independent switch. If the television turns off, the refrigerator keeps running.
And homes typically divide this distribution into 2 separate load capacities, too.
They do. There's usually a 15-amp circuit, which has thicker wires meant for heavy-hitting appliances like air conditioners or water heaters that draw a massive amount of current.
And then a separate 5-amp circuit for the lighter daily loads, like light bulbs and phone chargers.
But alongside the red live wire and the black neutral wire, there is a third, critically important wire in your wall.
The earth wire, usually covered in green insulation.
Yes, the green earth wire.
Now, this wire is connected to a literal metal plate buried deep in the dirt, somewhere near the foundation of the house.
It really is.
I just find it endlessly fascinating that our most advanced electrical networks rely on burying a piece of metal in the dirt to prevent catastrophic accidents.
Mm-hmm.
Why use the literal earth outside for the green safety wire? What makes the dirt so special for the safety of my toaster?
If we connect this to the bigger picture, it comes back to the concept of potential and resistance. The Earth itself is essentially an infinite reservoir for electrical charge. It operates at zero potential. Now, think about an appliance with a metallic body, like a toaster or a clothes iron. Over time, the plastic insulation inside that appliance might melt or fray,
Allowing the live, high-voltage wire to directly touch the metal casing.
Exactly. And if you walk up and touch that casing, your body, which is full of water and conductive electrolytes, suddenly becomes the easiest, lowest resistance path for the electricity to reach the ground.
Oh, so you become the pipe. And you get a severe electric shock.
A very severe shock. The green earth wire is designed to be a better, easier pipe. It connects the metallic casing of the appliance directly to that buried metal plate.
Because copper wire has vastly less resistance than the human body.
Yes. So if the live wire touches the casing, the rogue electricity takes the path of least resistance. It instantly rushes down the earth wire and into the ground, bypassing you entirely.
So the appliance's metallic body remains safely at zero potential.
Exactly. It's basically an express lane for disaster aversion.
Wow. But the earth wire only protects you from metallic casings, right? It doesn't protect the house from the wiring itself catching fire.
No, it doesn't. That happens during a short circuit.
How does that work?
Well, if the plastic insulation on the red live wire and the black neutral wire gets damaged, and those two bare wires touch each other directly, the resistance in the circuit effectively drops to zero.
And without the resistance of an appliance to slow the flow, the current abruptly skyrockets.
Right. A massive flood of electrons surges through the copper, and as those electrons move, they violently collide with the atoms of the wire.
And this atomic friction generates heat.
A lot of heat. This phenomenon is known as Joule heating.
Oh, Joule heating is the reason an incandescent light bulb glows, isn't it? And it's the reason the coils in your toaster get bright red and hot.
Yes. But during a short circuit, the Joule heating inside your wall wires becomes so intense that the copper can literally melt, igniting the surrounding wood and drywall.
Which is why the electric fuse, or, the modern equivalent, the circuit breaker, is an absolute necessity.
Right. A fuse is this incredibly elegant device designed to use Joule heating against itself.
A traditional fuse sits at the start of the circuit and contains a very thin wire made of a specific metal alloy with a low melting point.
Exactly. So if a short circuit occurs, or even if you dangerously overload a socket by, say, plugging in 4 space heaters at once,
The sudden, massive spike in current causes an immediate surge of Joule heating.
yes. And because the fuse wire is so thin and has a low melting point, it heats up much faster than the thick copper wires hidden in your walls.
So the fuse wire literally melts itself in half.
It does. It physically snaps the line and breaks the electrical circuit in a fraction of a second. It intentionally destroys itself to cut the power before the wires in your walls can reach a dangerous temperature.
It sacrifices itself to save the structure.
It's a lifesaver, literally.
Wow. So, tracing the path backwards, we can really see how an entire invisible ecosystem operates around us.
It really is an ecosystem.
We started with Hans Christian Ørsted, noticing a compass needle jump, which proved that electricity generates magnetic force.
Right.
Then we mapped the non-crossing field lines that reveal the strength and direction of that force. We looked at how twisting a wire into a solenoid creates a powerful electromagnet with a vital off switch.
Don't forget the physical push.
Oh, exactly.
Yeah.
We applied Fleming's left-hand rule, using interacting magnetic fields to physically push wires and spin the motors that power our lives.
And finally, we tracked that massive electrical pressure right into our homes, where parallel canals of power are kept safe by the zero potential of the Earth and the sacrificial melting of a tiny fuse. It's a perfect cascade of physics. But I want to leave you with one final thought, tying the macroscopic power grid right back into the microscopic biology we discussed at the very beginning.
Oh, bring it a full circle. Let's hear it.
The medical data is clear, right? Your nerve impulses continuously create tiny billionth of the Earth's strength magnetic fields inside your brain and your heart.
We are surrounded by our own internal magnetic weather system.
Exactly. Now, consider Ørsted's compass. It was sitting peacefully, pointing steadily north, perfectly aligned with the Earth's natural magnetic field.
Right.
But the moment a new artificial magnetic field from a nearby wire was introduced, the needle violently deflected. The new field overpowered the old one.
Wow. Okay, I see where you're going with this.
Given that we are now permanently living inside a dense, invisible web of powerful artificial magnetic fields emanating from domestic parallel circuits, spinning electric motors, high-voltage power lines, it raises a really profound biological question.
What's that?
Could our delicate internal human magnetic fields be interacting with this dense artificial environment in subtle microscopic ways we haven't even begun to fully map out?
Oh, wow. If a live wire can physically push a compass needle, what invisible forces are pressing against the electrical impulses inside of us?
It's certainly something to ponder the next time you plug in a fan or flip a light switch.
You are not just closing a circuit. You are actively altering the invisible magnetic landscape of the room you are sitting in. Keep questioning the invisible.